one. Okay. Okay, so just to make it bigger here. Okay, yeah. Okay, so again, okay, so just to refresh from yesterday's lecture. So I'm gonna make it bigger there. So this is an absorption column. So the absorption column is it should be tall, and then for the exam, for the module 2 exam, for the absorption, we would like to know how to calculate the height of the absorption. Okay, yeah. So because the absorption is actually based on the contact between the gas and also the liquid. So for example, if we want to have this purity of gas, how uh, how much is the height, is this required for the absorber column? Okay, and if we check it here, okay, and because in absorption column we have those little packings for random packing, so the gas so the contact is actually only between the gas and also the liquid there. Okay, so this is gonna be the contact, okay, the contact area, and every this one, every sorry, which one? Okay, and every random packing is also have their own we call it a coefficient of mass transfer, and also the wetted area yang terbasahi. Okay, so now let's have a look on the next slide. Yeah. Okay, so usually we use random packings, and then the packing sometimes it can be divided into two column, two pack or three packs, because sometimes we have a channeling. Channeling means when the liquid from the top just go to the sides. Yeah. Sorry. Okay. Uh, okay. So if the if sometimes if we have the liquid there, sometimes the liquid is have the channeling and just want to go to the this sides, yeah, around the close to the wall, while for example, where is it? Okay, but and wait. Okay, for example, the gas, for example, this one gas, usually the gas would like to be in just in the middle usually, yeah. So that means if the gas in the middle and also the liquid just around the wall here, so there is no contact between the gas and also the liquid. Okay, uh, so and then we don't want that. We want to have a good close contact between the gas and the liquid as well. Okay, yeah? So because of that, usually there is a maximum height to diameter ratio for the pack column, and then after that we have to stop the pack column and then put it a support there, and then after that there is a redistributor. Okay, there is a redistributor, start again, so all the liquid is distributed again, this area, okay, and then the gas also distributed again. Okay, so if we go back to the previous one here, the okay, this one. Okay, usually in yeah. So the one in here is called the distributor. Yeah, this one is the liquid distributor to distribute all the liquid to make it like a dripping, like a rain, for example. Yeah, it looks like a rain. Okay, but after a while, there would be channeling. So in here we have the liquid rare distributor again. Okay, so we have another liquid rare distributor again. This one is just to show you a different type of liquid rare distributor. Okay, if you have a very sophisticated rare distributor, maybe the contact would be good, but sometimes it gonna cost for the pressure drop, yeah, the pressure drop in the equipment, so we have to add the pressure drop. Okay, let's go back, just wait for a minute. I'm gonna put it there, and let's go back to the second one there. Okay, so now for today, what we're gonna do is we're gonna know how to calculate the height of the absorption. And then okay, also in the chemical process equipment in the volume 6, yes, CNOT, Colson and Richardson chemical engineering, you can also see many types of distributor, also the distributor, and also the hold up and so on. Okay, because after this you will also have the pack column design. So as the student outcome for a Bachelor of Chemical Engineering, you should be able to select the design. Yeah, so select and then apply the design into your problems like you're doing right now, yeah, with tray column. Okay, now let's have a look about the mass balance of the gas absorption. Okay, so in gas absorption we have the mass balance, okay, the differential mass balance. First we have gas from here, from the bottom, so that's this gas in, and then here is this is the gas out. Okay, and then also there's the liquid in, so the liquid actually the solvent that we use to absorb the gas, and then from the bottom here there would be the liquid out. Okay, so what happens is in every stage, from each stage there, the gas will contact with the liquid, and then the solute concentration on the gas will be absorbed by the liquid. So as it goes bottom here, the liquid will have higher solute, yeah, and then here the gas, it will leave out with a clean gas, because the solute that we would like to get rid of is actually absorbed by the liquid. So that's the basic idea. Okay, so right, let's have a look at one there. Okay, so how are we gonna say it? I'm gonna write it back here. Okay, so the gas in is called G. Okay, so and G is actually G is a molar gas rate, yeah, or gas molar rate. Right. Okay, so G is the molar gas rate, and but we also have G dash, yeah. G dash is actually the inert gas molar rate. Okay, later on in the calculation we're gonna use this G for inert gas, because it's actually constant along the column, while in the if we use molar gas rate, it's gonna be changed along the column. Okay, remember, because let's have a look about the example and the previous for yesterday. Just wait for a minute. So I just want to show you this one there. Back to here. Okay, so if you remember from yesterday's topics, if you look at here, if we look at the mole fraction of sorry, for example, the molar rate of all of the gas, for example G, so then we have to sum it up, all of them. Okay, I don't bring calculator with me, but let's have a look. Let's have a quick calculation. Okay, so we have argon 6.9 plus O2, yeah, oxygen 14443, and then the nitrogen, and also the water, and also the acetone. Okay, so the G is, if we add all of them, the G is 702.5. Okay, that one, per kilomole per hour. Okay, but there is another there's also quantity, we call it G dash. The G dash is the one that's also in the inert. Okay, the inert here is actually this one. Okay, so argon, CO2, nitrogen, and water. Okay, in this case the water is slightly increased because the liquid also is water, but let's say the water is doesn't increase. Yeah, so if we add it here, so that would be 6.9 plus 144.3 plus 536 plus 5. Okay, so this is about 962.2. Okay, yeah. Okay, so with assumption that the water doesn't increase, see over here the water is increased from 5 to 2 here. Around here it doesn't really increase, so the argon is the same, the oxygen is just slightly decreased, very slightly, and the nitrogen is also slightly decreased. Yeah, okay, so let's calculate. This is assumed constant. Yeah, okay, so 6.9, sorry, I just gonna start from the beginning. So 6.9 plus 144.291 plus 533.8. Okay, so I got this, the G dash over here is 692.174 kilomole per hour. Okay, so this is assumed that the water doesn't add it into the exit gas. Okay, so here we can see that if we use the G dash, or if we use the inert gas flow rate, so G dash is the inert gas molar rate. Yeah, the input over here is also 6.2, and the output is also 6.2. So it is would be a constant along the around constant. Yeah, constant along the absorption column. Okay, but if you check the G, for example, so then that would be 6.2174 plus 0.05. Okay, so this would be 6962.224. So the G over here, the G input, yeah, and the G output is different. Okay, because some of the solute, some of the solute, it has been absorbed into the liquid. Okay, so then the G dash, or the inert is similar, so that's why we will use the G dash. Okay, so here usually we use this G dash, or the inert molar gas rate, okay, inert gas molar rate, which is around constant along the column. Okay, and so if we use G, or the one that's changing for the liquid, we also use the L. Okay, but if we use G dash as the inert gas flow molar rate in the mass in the mass balance, we also use the L dash. And there's one more, which is called the superficial molar gas inner rate, which is the G divided by the G dash divided by the cross section of the column. Okay, sometimes we use this one as well, the superficial molar rate of the gas rate. Okay, so this is called G dash will similar to the liquid one. Okay, and now so that is the basic. So for example, if I'm gonna use this one here, okay, so if I'm gonna use G dash, then this also gonna be the G dash, and this also gonna be L dash. Okay, but the difference is later on is the solute. Yeah, the solute would be, the concentration is gonna change. Okay, so and then we also have this one, the solute rate, laju solute, ya, laju flow solute, is actually the concentration and multiply with the rate, or the flow rate. Okay, yeah, with the molar rate. With the molar rate. Okay, so the total molar rate is actually the inert and the solute. Okay, and also the concentration is also solute divided by inert solute, which is called mole fraction. Okay, so we also have small x, which is the solute divided by the mole of the inert and with the solute. We know that, yeah. Okay. Now and also we also have a mole ratio. Yeah, the mole ratio, we call it a large, yeah, or an alphabet, or no, a capital. So for example, if small x, or the mole fraction of the solute in the liquid, is actually the, for example, mole fraction A divided by the inert, and also plus the solute, yeah, the A. The mole ratio, so this is mole fraction. The mole ratio, we call it large X, yeah, and the large X is actually it's actually the solvent. So I'll say the solvent is A, yeah. A divided by the inert. Okay, so why? Because later on we can calculate with the inert basis, yeah. So later on we're gonna learn about the inert basis. In the inert basis, then the denominator, pembaginya, is the inert one. Okay, so the mole fraction here, this is for the gas, yeah. For the gas, the mole fraction is called Y, yeah, small y, which is actually the A divided by the I is the inert plus the solute itself. Okay, and there's another one is called mole ratio, which is the Y capital equal to A divided by the inert. Okay, so all of them is the same, just applied to a different topics, yeah. X is for the liquid, and this one is for the gas, yeah. Y is for the gas. Okay, if we use mole fraction, then we have to use the G, or the mole ratio, molar rate of the gas. Okay, but if we use mole ratio, because it is divided by the inert, then we just need to multiply it with the molar rate of the inert gas or inert liquid. Okay, so this, and then there's also there is a correlation between the mole ratio and also the mole ratio and also to the mole fraction. Okay, I'm gonna go back here. So maybe just add one more slide. Okay, just to make it easier to calculate. Okay, so we know that mole fraction, for example, for the gas, yeah, is called Y. Okay, and Y is actually the solute, for example, A divided by I plus I. Okay, while however the second one is we also have another quantity called mole ratio. We call it with the Y, the capital is actually A divided by I. So there should be a correlation between small y, the mole fraction, and Y capital or mole ratio. Okay, so here, for example, we can just to membalikkan ya, make this one, for example, with the let's put it conversely, dibalikan. For example, from here 1 divided by small 1, for example, it become 1 over y plus I divided by I, for example, sorry, I'm just gonna erase it. Okay, this equals to I plus A divided by A, yeah, just to convert this one, yeah, hanya dibalikan. Okay, and this equal to I divided by A, this plus this one also just subtract it, A plus A. Okay, and this is equal to 1, and this is equal to I divided by A is actually 1 over Y. Okay, so we can get the Y is actually 1 plus Y divided by Y. Okay, so there is a correlation between the mole fraction and also the mole ratio. Okay, so later on, if you have for example, I know the mole fraction of a solute in the solution in the gas, for example, you can also convert it into the mole ratio. Okay, by this by derivation to get this one as well. Okay, and then it is written in here. Okay, so the correlation between mole fraction is this one, yeah. Okay, and with the similar one, we also can get, so this is apply things to the liquid. So the capital X is actually the mole ratio equal to X divided by 1 minus X, and also the smaller one is actually the capital 1 divided by 1 plus. Okay, this is also the same, yeah. And also with the Y, so if you want to have the capital Y is actually the Y divided by 1 minus Y, and then the small x is actually capital small y, sorry, it's actually equal to capital Y divided by 1 plus capital Y. Okay, so it's similar with this one. Okay, so that's the thing. Okay, so then so if we use the rate with the inert one, the inert basis, then we have to use the G dash and or G slash dash. Then we use the molar rate, molar ratio. Okay, we use the molar ratio. Okay, sometimes in very often it is very dilute composition. So sometimes the amount of mole ratio of in the gas or in the liquid it can be similar to the mole fraction if uh, the solution is very dilute or encer, yeah, very dilute. Okay, now we know the concept of G, and also oops, let's have a look just to have an eraser there. Okay, now we know about the concept of G. We also know the concept of G dash. We also know the concept of G S dash. Okay, just maybe just quick asking. Who want to ask? If you who listen to this one. So do you want to know? Who want to give some definition? What is G? What is the G dash? And also what is G superficial? Let's check. Gamma, would you like to? Gamma Rafani, would you like to a little bit sum up? So what is G? Gamma, are you listening? Right. Not listening. Alisa, are you listening? Alisa? Hadian, are you listening, Hadian? Hello? Helena, are you listening?
Yes, po.
Yeah. So what is G?
G is the total molar gas flow rate, right? If I'm not mistaken.
Okay, good. Total molar gas rate. What is G dash?
It's the inert one.
Yeah, the inert one. What is GS?
It's the superficial one, which is the G divided by A, if I'm not wrong.
Okay. Yeah. So the G is divided by A. Yeah. Okay. Good. Okay. So that is the one. Yeah. So that is the concept. And the second one, we also know about the. We should know about the difference of the small y and also a capital Y. Okay. Who want to just want to check again? Dia, are you listening? Dia, are you listening? What is Y? Damalia, are you listening? Hello?
Hello, can you hear me?
Yeah. What is Y?
Y is the mole fraction
Yeah, good. Mole fraction of what? Or gas or liquid?
of
Y is always
the
for the gas.
gas.
Yeah. Y.
Of the gas.
Yeah, the convention Y is always for the gas in any liquid, gas or liquid vapor. Yeah, gas or vapor. Okay. How about the capital Y?
The capital Y is the mole ratio
The mole ratio
of
of
gas.
okay, okay, right, okay, right. Okay, thank you for Helena and Dama who answered my questions. Okay, anyone just a little bit of tips, yeah. If you think you're not listening, or if you think you're not in the mood of learning, let's say, um, what you can do is you just don't need to come to the class, yeah, because that means you have 2 times of learning, right? The one that listening with Bu Winnie now from 9 to 11, but you don't understand anything. But then you have another homework to listen the recording, right? So I still I have a little tips, yeah, since I was in a students, yeah. I was also a student of this, of course, from ITB, yeah, angkatan 2002. I also was very actively in Himatek at that time. Yeah, I was the for the human resource sumber daya, and also at that time I teach, yeah, I taught high school students to earn my money, yeah, to earn some money, uh, because my mom at that time only giving me about 5.000 rupiah, ya, at that time. I think it's just very very small, yeah. And then so I earn more money with tutoring high school students with my motorbike at that time. Okay, so I have to do the management at that time at the third year. And I also I can't I need to sleep, yeah, at that time. I need to sleep like 6 to 8 hours a day, okay? And then, of course, as a student, it's very, very difficult, because if not, then tomorrow, the next day, I would be very, very, very dizzy, and then headache and so on, okay? So, at that time, when I was in your age, I try to listen what the students, what the lecturers say at that time. Okay, so I don't need to uh, do my homework again to open the books, or open the PPT, or open the slides, or open to everything. Okay, or if I don't understand, what I do is what I did at that time is I asked my friend who is maybe smarter, yeah, a lot of smarter people in chemical engineering at that time, of course. So I asked them how to solve the problems if I don't understand. Okay, so I think that's one of the tips that I don't know for now. I really sure that you don't read the books, right? You only just watching the recording, or the PPT, or yeah, just check that one, or maybe and also writing notes as well. Okay, so I think, but and also asking the lecturer is much better compared to you don't understand, or you don't understand what I'm saying, and then you just keep it. Okay, later on I can learn it. Okay, so I think this is just my little tips for you, because to be honest, the one that we give it to you is a very like algorithmic, yeah, 1 by 1 2 3 4 5. So we give all the steps, right? 1 to 10, for example, and then for the module it's just exactly the same. Okay, there is no room for thinking how if this, how is that. Okay, that is not the syarat kelulusan. Okay, so I think you're a very yeah, you're a grown up, of course. Of course, you're an adult now, and then you should know how to maximize your potential, and also use your mind, your mom's and dad's money wisely, yeah, because of course you pay a lot to be in of course this is an international class, so it takes a lot. Okay, so just few tips. Yeah, if you say that, okay, I want to, so don't uh, go to a lecture because we told you so. Okay, if you want to go to the lecture like 9 to 11 and then you just can wake up around 8 something and then just and you also doesn't open your camera, so you don't have to put your hijab on or have a good makeup or something, right? So you just can just listen, but I think it's very important if you can try to listen, and then you will not be, yeah, so you can have like more sleep, okay, more time for do things that you like, yeah, do socialize and so on, okay. Just a few tips for me. All right, let's continue. Okay, Helena and Dama also just mentioned about the GS and LS, or maybe same with LS, yeah, and also the mole ratio and also the X. Okay. Now, just asking a little bit, okay, to who is it's this very small one, okay, because it's only like 7%, and then usually in the class we can just have a round, uh, yeah, like a round table, and then just ask everyone, okay, because just to make sure that you're learning in the same direction, okay. Right. Okay. Who hasn't asked? Okay. Uh, Fatia. So, uh, the GS, is it GS dash? Is it constant or is it changing?
If I'm not mistaken, it's constant.
Yeah. Why is constant? Because it is only the inert, yeah? Isn't it?
Yes, ma'am.
Okay.
Yep.
So in previous slides, I tell you about there is a G, which is the gas molar rate, and then also the G dash, which is the inert, only the inert. Okay, so if we use the G S dash, or the superficial gas molar rate, is this also constant from this one to this one. So then if we only have one value, we don't need to find this value because this is constant. Okay, that's also applied as well to the LS there, yeah. um, in the LS also we have the LS is the constant, over here on the output is also constant. Okay, so the one is changing is only y1 and y2 and the next two and the x. Okay, and it's changing like maybe like a curve, yeah. And then and this tells you about the position in one position of the height, what is the composition of y and the x. Okay, so that should be make us easy, because if we have if we use G over here, then it's gonna always changing, so it's gonna be difficult to maybe later on to integrate. Okay, now let's have a look on the mass balance. Okay, let's us check this envelope over here. Okay, and then let's put the one who just put into those envelope. This one is y1 multiply with gs. Okay, and then also the one that's put inside is the only this one should be goes up, yeah. This one, there's one there, yeah. And then the one that's goes inside is also the ls dash with x. Okay, this is the input, and then the output one is the y multiply with gs dash plus the ls dash multiply with x1. Okay, this one. Okay, so this is the mass balance. Just close the video then. Yeah. Okay, now this is a constant. Y1 also, we know the y1, yeah, we know the input, so we know this number. X, we don't know x, yeah, x is a variable. I'm gonna write this. Okay, because x is would be along this one or this one or that one, we don't know, yeah, just a typical position around here. And then equal to gs dash multiplied with y plus s dash multiplied with x1. Okay, so then let's just rearrange this equation. So let's make the y is around here. So here we have the ls dash and x, and then the number or the constant here, because constant, let's group in one way there. Okay, and then so we have y as a variable, and also x a variable, only power to the 1, yeah, pangkat 1, and also there's a constant. So it looks like and then we can just divide both of them, yeah. So we can divide both of them. So then we have an equation, it's called y, okay, equal to ls dash divided by gs dash of the x, okay, plus of that one there, yeah, g s y1 minus ls1 x1 divided by gs. Okay, so this tell you it looks like a gradient of the x and then plus a constant, and this is equal to an equation. Okay, so that means the this one here, we can find any y or any x if we have another one. Okay, if we know the y along the height, we can also find the x. Okay, and so this is an equation, and it looks actually similar with the distillation because it is called the operating line. Okay, so the correlation between x and y, yeah, y and x in a mole ratio in one point is called operating line. It's just similar, yeah, with the distillation as well. In the distillation as well, we can find the correlation between y and x in one row. Okay. Okay. So again, so this is a straight line equation in the y versus x diagram. Again, look, this is a capital, so you have to ensure that you should plot the mole ratio, yeah, not the small y and small x, not the mole fraction. Okay, and also the slope, this one, the slope, oops, yeah, the slope is ls over gs dash, yeah. So that means that ls and over gs dash is actually the slope. Okay, so we can change the slope of the operating line if we change the ls or the gs. Sometimes the gs is also defined, yeah, the gs is defined because we know the feed from the previous stream. Kita tahu berapa gasnya, ya, gasnya nggak bisa diubah, ya, because that is the one that we want to treat, yeah, the one that's gonna be the treatment is the gas. Okay, the one that we change later on is the liquid. Okay, later on it will impact into the height. Sometimes if you want to high height, then higher height, then you can have a smaller liquid maybe, or but if you have if you don't want to have a high height, just a very low height, for example, you can just add more solvent. And the solvent itself, the ls solvent, later on will be correlated into a capital cost or operating cost. What do you think? The liquid. What do you think? The liquid is actually, it can be correlated into capital cost or operating cost.
Is it operating cost, ma'am?
Yeah. Okay. Of course. Yeah. That is gonna be operating cost. if we have the solvent as a water, it's easy to recycle, okay, and then it's fine, okay, or maybe very small. But sometimes we I have research on rare earth metal, or yeah, about rare earth metal, and then how they, if we want to have a contact between the liquid, and the liquid is actually is very expensive. It's like organic and organic solvent, and also proprietary ya, mahal, and ada mereknya ya. So that means if you have too much solvent, and the solvent, for example, can't be recycled back, then you will end up with many solvent that you need to use for the absorption column. Okay, so so this graph, or this slope later on is gonna be later on will be affecting on your operating line. Okay, remember, we are a chemical engineers to be, ya, we're calon teknik kimia ya, engineer teknik kimia. We don't only calculate things, but we also think about the impact of our calculation. Okay, as a chemical engineering designer, when we design the plant or design an equipment, we have to consider everything, including the operability, and also the cost, and so on. Okay, so back to here. So it is a straight line in the y and x diagram. So y equal to L S g s dash of x plus blah blah blah, yeah, and this one is the slope. Okay, so this is called similar to distillation analysis, where the equation, so we have the operating line. Okay, now in the distillation we have equilibrium, we have also operating line. Okay, in equilibrium, for distillation analysis, we can find the equilibrium between vapor and liquid. Yeah. Now, how about the equilibrium in absorption? Yeah, that's a question. And then if we go back to yesterday's lecture, you will also know that for the absorption column, we can use equilibrium for using the Henry's law. Okay, remember, and the Henry's law is actually equal to pi with the constant of the Henry constant of the xi, which is this equal to the yi, or the mole fraction of the gas, multiply with the total pressure of the system, is a coefficient, and also the xi. Okay, so because this one is using small y and also small xi, while we use the mole ratio, not mole fraction, so later on we need to change this into y and change this into x, yeah, this one. Okay, and then usually the Henry's law, we will find the coefficient in the problem, yeah, this all. Of course, so in any type of contact between gas and liquid, they have the value. Okay, they also get the value from experimental for experiments. Okay, the total is from the p of the total, yeah, the total. And then how to get the p total? Usually we this is also, you can get the pressure from the gas equation, PV and RT, yeah. So if you have a volumetric rate of the gas, you also know the temperature, and also you know the how many kilomole of that one there, you can get the pressure. Okay, so then you get that one. Okay, so based on here, then actually the structure that we gonna solve is really similar to the distillation column. Okay, we have equilibrium, correlation, and also operating line. Okay, so this one is the the equilibrium curve is not linear, so it would be look like this. Okay, so this is the equilibrium, and then later on we will have also another the absorption operating line by also with the equation of the mass balance. Okay, now the problem is here's the thing. So let's have a look on a certain height. Okay, go back to the column, yeah, the absorption column. You have the column there, and in one certain height you have the gas coming out to the top from the bottom, and the gas has the GS dash as the inert flow, and then with a mole ratio of Y. Okay, so if you multiply the mole ratio of gas multiply with the GS, then you can get the molar rate of the gas in superficial. For the liquid, it's also similar. You have LS, and then also you have X. Okay. Now the problem is, so this one is the correlation between Y and X. The correlation is operating line. We know the correlation. Okay. Now for the equilibrium, absorption between the gas and liquid, the equilibrium is only on the interface. Okay, so this is actually what happens on the mass transfer. Okay, please have a look and then just listen a little bit. Yeah, I'm gonna try to explain it slowly. Okay, so the gas in the bulk phase, fasa curah, yeah. In order to contact with the liquid, they have to get a transfer first into the interface. Okay, so this is the mole ratio in the bulk phase. They have to transfer it in first into the interface, which is called YI. Okay, the rate of transfer, jadi dia harus nempel dulu gitu ya. And the rate of transfer here is called the mass transfer of the gas. Okay, this is called the mass transfer of the gas. Okay, and then we know there would be a calculation of that one. Okay, if the mass transfer coefficient is high, then it's just very easy to go into the interface, and sometimes because of the usually because there's also resistance, of course there's a difference between Y and also YI. Okay, and in this YI, the gas in the interface, then it will have an equilibrium with this one, so it's gonna transfer into the it's gonna start dissolve into the liquid. The composition of Y when it dissolves into the liquid is called Xi, which is the equilibrium correlation of absorption. So Yi and Xi is the equilibrium correlation, but still in the interface. Yeah, it's still in the interface. So Y in here, it will be correlate with the X here. That is the Henry's law. Okay, and after that, once it has dissolved with this concentration means it's increased. Yeah, this is tell you about it's gonna be decrease a little bit the value, but then it's gonna increase like that. Okay, And after that, from the interface, the liquid will be transferring out. Yeah, the solute will be transferring out into the liquid phase. And then because of the transferring out, also there is a resistance and so on, and then there would be a difference between xi, or the x in the interface, and also the x in the bulk phase. Why there should be a difference? Because in order to have a mass transfer, if this xi equal to x over here, so there's nothing here, okay, the mass transfer is stopped. So usually the x of the bulk phase should be lower than the x in the interface, so then the x or the solute in the interface can move into that one there. So that is the mass transfer from the gas into the interface, and then from the interface into the liquid. Okay, in chemical engineering we use this a lot, this phenomenon a lot, because of course in chemical engineering everything is about transfer between a gas to liquid, liquid to gas, or gas to solid, solid to gas, and so on. Okay, now the one that we know the correlation of this one. Okay, and we know the also correlation of this one between the y and also the x, but we don't know the correlation between y to yi, and also we don't know the correlation between x to x, xi to x. Okay, so that's going to be a little bit of problem, and then let's have a look. Okay, so okay, just make it smaller there. Okay, so here, so in some points, for example in these points, okay, we know the correlation of y and x with this red dot. Okay, we can read into here is the x, and read to over there is the y from the operating line, because there is a correlation between x and y. Okay, and we know the correlation of yi and also xi over here. Let's say I'm gonna write it with the, maybe with the blue one. Okay, with the Henry's law, with the equilibrium correlation, if we have some points of y, we can also get the x, or if we can get the x, we can also get the yi. Okay, but what we don't know is we don't know the correlation of this one, yeah, of this line. We don't know this one, yeah. How we know the correlation y to yi, or the correlation the x to xi? We don't know that. Okay, now to solve that, we have to think about mass transfer. Okay, so in mass like you haven't learned about mass transfer, you will learn that in transfer phenomena next semester. But we know that there is for mass transfer, the driving force is the difference between y and yi, the bulk in the interface, and also the bulk in the interface. Okay, yeah. Okay, so right, so go back here. Now let's have, but before we talk about the mass transfers, let's have a look about this graph first. We can start to put everything on the graph. Yeah, let's say around this area here, the y wait, yi is equal to xi. Okay, yeah. So yi is equal to y1 equal to x1. So that means this one it start with the high gas, yeah, over there. So this is the high gas. So that's why the value is higher. It's gonna start from here, from number one, and then with the some maybe with some x, yeah, with some with it is paired with x, and the x is the solvent that have a solute, and then it will have some enriching, yeah, from here. So this is the x1. Okay, so one line over here, the correlation between y and x, it can be represented by 1 point. Okay, how you read them, it looks like in the distillation, horizontally you can read the value of y, vertically you can look the value of x. Okay, and as it increase, the liquid will absorb the liquid, the solute, and then the concentration of y is actually going to decrease. So it's going to decrease, and up to the output, yeah, to the outlet, for example, y2. Okay, and then this one is the fresh solvent, yeah. Sometimes the solvent still contain a little bit of solute, so the number is not 0. But if you started from fresh solvent with there is no solute at all, you can maybe up to over here. Okay, so and then this is your operating line, yeah, where is you know that the y equal to L dash S over G dash X plus blah 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 blah. Okay, yeah, and also that is for the intercept. Okay, but the slope for the operating line is LS and over GS. Okay, so in sum up, the operating line is the relationship of concentration y in y gas with the concentration of the liquid x at a certain height. Okay, this is typically tells you the concentration of y and x at certain height. So it's gonna move from x1 and y1 over here from the input, yeah, from the top, and then moving down the word there to the outlet, the outlet or the liquid in. Okay, and certain point 2, we also have, this is why we also have at a certain point we have also concentration profile like this, and then we know that yi is equilibrium with xi. Okay, so it's gonna be looks like this. Okay, this is when yi less than y and also xi is more than x. It would be looks like this. So there is an equilibrium and also the operating line. Okay, now the problem is, like we talked before, is actually what is the difference, what is the correlation between the operating line and the equilibrium line. Okay, in the distillation it is quite easy because you know, for example, the distillation, yeah, or from operating line, this is the equilibrium line, and then operating line again, this is equilibrium line, and so on, right? That's in distillation, if you remember. But this one we don't have much understanding for now. What is the correlation between the operating line and the equilibrium line? Sorry, not the equilibrium line, but equilibrium curve. So now what happened is, now I'm gonna explain to you about the concept of mass transfer. Yes, I think I need to read it. Coefficient. Right. Okay. So again, uh, this is similar with the previous one. So the solute transfer from the Y into the interface, okay, from here to here is called the from Y to YI is called the mass transfer of the gas phase from bulk to interface, ya, from the bulk phase fasa curah, ya, to the interface. And the rate of the mass transfer, the rate laju perpindahan massa, the rate of the mass transfer is actually the driving force divided by the resistance. Okay, and 1 over resistance equal to coefficient. The concept is similar with operasi perpindahan kalor, ya. In if you remember the Fourier's law, ya, Fourier's law, you know the Q equal to minus K, and then multiply with the delta for the conduction, for the heat transfer, T, yeah, remember Fourier's law. Okay, and for the mass transfer, it's called a fixed law. You will learn later on, and then it's actually, we called it JAB. It's actually minus of the K, or the coefficients, and then the driving force is the delta concentration. Okay, the concentration, and or the concentration at this in this case is this one, the mole ratio. Okay, so this K is called KY if because it is in the gas phase. Okay, so here, oh, it's not JA, NA, sorry. Just put it. Okay. Okay, so here for the mass transfer, the N, yeah, or the mass transfer rate, yeah, the mass transfer rate multiply with A, with the because this N is the superficial, yeah, multiply with A, is actually equal to KYA, or the mass transfer coefficient in a gas phase, multiply with A, the area of mass transfer. It's not the cross-sectional area, ya. It's the area of the mass transfer, area yang terbasahi. Multiply with the driving force. And the driving force to do the mass transfer is the driving force, which is the difference of the concentration in the bulk phase and also in the interface. Okay, and this one is actually the the Y minus YI. Okay, and so once it goes into the gas phase, after that they gonna dissolve into the liquid phase with the equilibrium composition, and after the equilibrium composition in liquid phase, and that is gonna be transferred out again, yeah, and then here we called it mass transfer of solute from interface to the bulk phase. Yeah, looks like how if we have a transport, kita jalan-jalan, ya, if you have a transportation, for example, let's say you go there with the bus into a terminal, okay, and in the terminal you have to change the terminal, maybe, for example, and then, or maybe, for example, you want to the airport, using, I don't know, using a bus, and then you go to terminal, and then from there you have using, I don't know, maybe airplane or something. Yeah, so it's like that one. There's what, step 1, step 2, and then step 3. Okay, then we have the xi minus x, that's also the driving force. Okay, with that similar topics, we can also write the mass transfer in the liquid phase. The mass transfer in the liquid phase is this one, okay, which is NA. NA is the, so I'm gonna write here, NA is the rate of A, yeah, of mass transfer. And then superficial, or we call it mass flux. Flux is if you have a volumetric and then divide by area, is called flux. Yeah, and so this is the mass transfer flux of the A. It's actually the A. I think I don't need to write superficial here, yeah, because the area is actually for the area terbasahi. Okay, equal to the here this one is called mass transfer coefficient in the liquid phase. Okay, and denote with X. Okay, so we have the mass transfer coefficient in the gas phase, and also we have the mass transfer coefficient in the liquid phase. Yeah, how fast or for how just it's not fast. Okay, how slow is the mass transfer, and then multiply again with the coefficient. With the area, and then multiply again with the driving force. Okay, now at steady state, NA in liquid equal to NA in gas. So in steady state, this actually should be the same, isn't it? Yeah, because the transfer from the gas phase into the interface, it should be the same with the transfer from the interface into the liquid one. Okay, so because of we have those two things here, then the process of transfer can happen. Okay, then we end up with this equation. This one would be equal to this one. Okay, so then we're gonna end up with okay, maybe just wait a little bit before that later on this one equal to this one there. Okay, now let's move to the next part, how to calculate the height. Yeah, to calculate the height, let's see, we have this is the height of the area, the height of the column, and then we just put, for example, up to here is called the height is Z. Okay, and then we just pick up just a differential of that one there from from Z to Z, Z to Z, yeah, to Z plus dz. So it's at height Z, small z, and the thickness of dz. Okay, and that with the area is the area of transfer of T in the dz segment. Okay, and the A is called the mass transfer area per volume bed. Okay, so A is actually based on the data packing, so it's specific for each type. So for example, for racing ring, and also for the saddle, for the pole ring, the previous one, yeah, for each packing, the random packing, they have specific mass transfer area per volume bed. Okay, and the bed value, bed volume is called the cross-section area of the column, and then we use superficial rates. So anyway, if we use the superficial rate area is 1, we got the area of transfer if A digit. Okay, now in order to get the height of the column, we have to do an integration. Okay, so for example, from if the A of the massa terbasahi ya, the area yang terbasahi, the area of all the packing, the contact between the liquid and the gas, and then A is equal to A, yeah, the area, and then multiply with the dc. So like the area multiply with the dc is like how much of the height. Okay, and then we have this the mass transfer. For example, for the gas, the Na equal multiply with A equal to chi y, the coefficient of in the gas phase, multiplied with the A, so we use the small a there, and then y minus yi dz. Okay, now so then to get this one here, and then let's check the mass balance. Yeah, so the mass balance, we have a gs with y. Okay, this is the input. Okay, and the output we have gs at y plus dy, that one there, plus the one that goes into the liquid phase, ya, yang transfer, NaA. Okay, and then we can change the NaA with this equation, and then move the NaA with this equation, and then this is G dash, sorry, I'm gonna make it bigger here. Okay, so this is gs dash y, this is gs dash y, so it cancel out and it become gs dy. Okay, so then we can get, and then we can rearrange this one, put it here, we can make it as, for example, just put it, so this is the dy, so we can get minus gs dash dy equal to kya dz oh sorry, just try to cancel out. Just let me write it again from here. From here, yeah, from here we have maybe put it over there, yeah, we have kya y minus yi of dz, yeah, this one equal to this, so it's a negative, so minus g s dash dy, and then we can put this one over here, so dz equal to minus gs dy there, divide by kya multiply with y minus yi. Okay, so this one. Okay, so then so we can calculate the differential of the height if we know the driving force, or the difference between the y in the bulk phase and also in the interface, and then also the gs and also kyi. Okay, now when we look at the equation, we can see if we can solve analytically or not, because this is coefficient, this is a variable, but this is a constant. Okay, and then some correlation. Okay, so we have to find the correlation of y and yi. Okay, so anyway, now we know that if we integrate it from to get the height, yeah, to get the height, so we just need to integrate this dz from 0 to height. For example, this is equal to the integration from y1 to y2 minus of the gs dash of chi ya dy yi minus yi. Okay, so this is how to get the height. Okay, we know the yi, so y1, sorry, we know y1, so I'm gonna write it here. So y1 we know from the problem. Okay, y2 we also know because it is the target. Yeah, y2 is the target. For example, I want to decrease the CO2 content from 2% to only 200 ppm. So the y1 we check from the mole fraction from, for example, 0.2% into 200 ppm. Okay, and then we change it into mole ratio, and then we can get the number. Okay, GS, do we know GS? Do we know GS? The superficial gas flow? We can, yeah, we may know, or maybe we may not know. Yeah, if we know the area or the cross-section area of the absorption column, we can know the superficial gas. Yeah, we can also find the superficial. So we know this one is a problem. KYA, it is given from vendor. Yeah, or sometimes, of course, would be also written in the problem as well. Why? Because in every packing column, in every random packing column, they have a unique KY and then multiplied with the A. So A is the wetted area, luas yang terbasahi, yeah. So for example, I'm gonna tell you the difference between the cross section, the cross-sectional area and also the A. So for example, we have this packing like that. Yeah, just in, for example, okay. Okay, so for example, this is the packing, and then they're gonna run an experiment to check if they have the liquid and also the gas, which how much is the area that has been wetted, di mana luas terbasahi, maybe from the liquid, maybe over here, maybe over here, and then it's flowing around here, flowing here, and then this one, and then flowing there, for example, maybe flowing over there, maybe flowing there, maybe flowing there, and then maybe flowing there. Okay, so they calculate with some method to find the wetted area. Okay, of course the one that inside here is not, it won't be happening, for example, but for example, if there is it can go inside, maybe there's the one that inside here, the one that inside here. Okay, so it's really basic how to so they have the A. So A is the wetted area. Usually they would say the wetted area, how many square meter per meter cubic packing. Yeah, so they will put this in a column and then check the volume, the total volume, yeah, termasuk ruang kosong, including the void area, and then they gonna do the run and then the test to get the how many square meter of the wetted area. So this one KYA sometimes it's just like in one quantity, ya, tergabung, because ky is the coefficients of the gas, and then it's also run with the test, yeah. And then so the vendor will say that, okay, so the ky for fluid, this fluid is this one, is this fluid is that one. Okay, they will give the data. We can't get that from books, yeah, from handbooks. Okay, so here we also is given, so this one is given and this one is given, and then also we have the height, yeah. And then now the problem is now is to find the correlation of this one, how to get the correlation of y1 minus yi. Okay, so next week we will continue our calculation, how to solve this problem. Okay, because we know the graph, this is the calculation, we know the y, we know the gs and also kya, but we don't know the correlation of yi, so y to yi over here, and how to get that one, then how to do the integration to get the height. Okay, all right, I'm just gonna stop here, and then I would like to ask if you have any questions regarding the calculation up to find the height of the absorption column.
Do I have a question?
Yes.
To calculate the superficial gas flow rate one, do you divide it with the cross-sectional area or the wetted area? Because I think both of them uses A, right?
Yeah, the cross section for this one, the superficial, this one.
Yes, Po.
Oh yeah, that one is for superficial. So for GS equal to G divided by A. A is the so the cross section, yeah. Cross section of column. So capital A is stands for cross section of the column. So if this is the cross section of the column, yeah, if this is the column, so yeah, this is the A, yeah, the cross section, which is P R square. But for the area of the contact, for the KYA, it is the wetted area, and the wetted area is going to be given. Okay, we will continue next week, but I think I can give you some examples of the problem, so you know what to expect. So give me a minute, let's have a look on maybe last year's topics, yeah, just to give you an idea. Okay, I'm gonna share the screen, but sorry, it's in Indonesian. Yeah, so this is the typical question that is 1 or 60. Yeah, so I'm gonna just a little bit of highlights. So for example, this is gas keluaran proses gasifikasi mengandung 10 mole percent of CO2. So and then it's gonna be cleaned by absorption. So what do you think is this one? Mole 10% mole of CO2. So this is gonna be the input for absorption, right? So is it a mole fraction or mole ratio? What do you think? All right, then we can continue next week. But anyway, this is the type, so I'm just gonna give some example. This one, for example, 10 mole percent, so it is mole fraction, yeah, mole fraction of gas in, so it is actually y1, small y, okay. And with this one you have to change into a capital Y, or to the mole ratio, okay. And then another examples, this one, they will tell you about KYA, but this is a capital K, so I'm gonna explain to you what is capital K next week. So, but it's actually the coefficients is gonna be written in the problems, ya, harga koefisien transfer solut keseluruhan, for example, okay. And then we also, for example, know the superficial gas. This one, for example, so superficial gas, you can change what is example. Okay. Anyway, we can have a discussion about this example, so you know what to expect. So the typical of the absorption is you have to know the height. Later on, I'm gonna explain to you about the theoretical plate, yeah, height equivalent to theoretical plate, and then also how much the cairan penyerap, yeah, how much L you need to do this absorption column, okay. All right, looks like it's almost 11 o'clock, so I'm gonna just leave it out for you because you're still doing the tri-column assignment, right? So let's continue to next week. We're gonna continue about how to solve the calculation to get the height of the absorption column. All right, any other questions? No. Okay. All right then. Thank you everyone, and have a good day and have a good weekend, and then we're gonna see you next week. Bye bye.